Hello, Physics Nation. My name is Nate Larmond, and I'd like to do this semi-atwood machine. This is one of the optional student practice problems. It's actually the first one on my list. And we've got a hanging block coming off this pulley that is tied by string to this other block. In this problem, there is no friction, but check it out. In video number 11 of the College Board Review series, there is friction. So is this coincidence, beyond coincidence? I don't know. Are these two people coordinating? Who knows? But this is a really common Newton's second law type setup. We want to see how mass and force affect acceleration, and you can do all sorts of kinematics once you know the acceleration. So let's see what this problem is asking us to do. It says, suppose the mass of block A is much greater than the mass of block B. Estimate the magnitude of the acceleration of the blocks after release. So much greater. Oh, first of all, the pulley has negligible mass, spins with negligible friction, and there is negligible friction between block A and the table. All right, so much greater. So I don't know what that means. 10 times greater, 100 times greater, a million times greater. They said don't use mathematical expressions. This is the qualitative part of the qualitative quantitative. So you're actually supposed to do this later, but I do the math immediately. This is an F equals ma problem. The force is the weight of block B. That's the hanging weight over here. So we just do mg. And the mass is both pieces of mass, mass A and mass B. They are connected by a string, so they are one system. All you do is divide both sides by the sum of the two masses, and boom, there's the expression for the acceleration of the system. So the deal is, if A is really, really big, this fraction approaches zero. So the bigger mass A is, the table mass, the smaller the acceleration. So I guess I just should have written the greater the mass of A is, the greater the inertia of the system, leading to a small acceleration. Is that good enough? I don't know. In the next video, I'll grade my work. We'll take a look at the scoring guidelines. Let's see what the next question is. Whoops. Briefly explain your reasoning without deriving or using equations. Right, so I would just say more mass, more inertia. Inertia and acceleration are inversely proportional. So as mass A approaches infinity, the acceleration of the system would approach zero. That's what an inverse relationship is all about. Now suppose the mass of block A is much less than block B. Estimate the magnitude of the acceleration. So really, this is why the mathematical model is so important. Now they're saying B is much, much greater than A. So that means this fraction approaches 1. That means the acceleration approaches free fall acceleration. So it's like this inertia, this resistance isn't even there. And that means there's no tension in the string, really. So it would be in free fall if this hanging mass were much, much greater than the table mass. Okay, now what? Free body diagrams. Okay, so the table has weight pulling down, normal pushing up, and the tension pulling to the right. The hanging block B has weight and tension, and that's it. So pretty simple free body diagrams. Now what would they like? Derive an equation for the acceleration. Right, so I started out with a derivation. Don't do that on May 17th. Do it in the order they asked for. Do not add anything to the figure in part B. Okay. So I already did this. This is linked up with F equals ma. All you need to know is the m is both. And the weight is mass times acceleration. Okay, so I'm running out of time. Let's see here. Oh, now we replace the original pulley, the massless pulley, with a massive pulley and explain what happens to the tension. So more mass means less acceleration, and I think that means T2 increases. All right, let's score this thing.